So speaking of phase changes, when we're discussing the latent heat of fusion, we're talking about either the energy cost to going from a solid to a liquid, or the energy saving of going from a liquid to a solid. And in the case of water, the latent heat of fusion is 334 joules per gram. Now, maybe this has occurred to you already, but solid and liquid are not the only phases. There is another phase, and that would be the gas phase. So if we're starting with a liquid and going to a gas, then there would need to be an energy expenditure as well. Or if you're going from a gas to a liquid, there would be an energy savings. This is also called a latent heat, but this one is called the latent heat of vaporization. Now, the latent heat of vaporization for water is substantially higher than the latent heat of fusion. The latent heat of vaporization, see F for fusion, V for vaporization, is equal to 2,260 joules per gram. That is nearly 7 times the latent heat of fusion. That is much, much higher. Right, so I want to give you a visual to kind of help you make sense of all this. I'm going to start with one phase on the left here, solid. In a solid, the particles are locked in a grid. They can't move relative to each other. So if particles are cars, a solid is kind of like a parking lot. So here's a little parking lot. There's the way in. And the parking lot, it's a very small parking lot. Just like 6 spots. Okay, so you can drive in and park here or park there. These are 6 parking spots in this tiny little parking lot, and that's the way in. Now, in a liquid, the particles do move faster, yes, because it's warmer, but they also are not stuck in a position. They can move freely. So I'm going to model that one more like the road that you could take that would turn into this parking lot. That is a quality cue right there. Okay, so if this is our solid, cars like particles locked into place, and this is a liquid in which they're moving faster, but also they are not stuck in a particular position. You know, they may get further apart or closer together, turn past each other, all that kind of stuff. The relative positions of cars on the road are much freer. If you're going to leave the parking lot, of course you need some speed, you need some heat, but you can't just go out. You need to be able to match the speed limit of this road. Normally parking lots have a speed limit of like 10 miles an hour. This road may have a speed limit of 45 miles an hour. It's not enough just to move out. You also need to be able to, you might say, compete with the traffic of this road. So you can kind of picture a car waiting here to get out, and as soon as an opening appears, he's got to kind of push the pedal down hard and gun it to get out without having to wait even longer. You can think of that as like the latent heat of vaporization. So let's get, the latent heat of fusion. Let's get to the latent heat of vaporization. So this road has a very sharp turn, and this road is going to go by the highway. The highway is kind of like the road in that The relative positions of particles / cars is not fixed. However, what makes the highway different is, one, that the lines are not nearly as neat. What makes the highway different is that the velocities are so much higher, and also because there's more lanes, there's a lot more freedom. Gases in reality can expand. Liquids are stuck in the bottom of a container. Gases expand to fill a space. So, the analogy is not perfect, but the idea is, let's say you're at the speed limit for this road, 45 miles an hour. That's not enough to get you onto the highway. So let me give you an on-ramp. And you're in Pennsylvania because there's barely any on-ramp at all. So the idea is there is a high speed limit for cars on this road. They're going 65, 70 miles an hour. And this car, in order to actually get up to there, needs to be able to speed up to match this. Now, in reality, if you've got the surface of some water, there are particles on the surface of the water that could jump into the air, except that there's already air up here. And they're already moving at highway speeds. So it's actually air pressure pushing down on the surface of the water that keeps water molecules from just evaporating straight into the air. Yes, you need to get water up to boiling point before they can move fast enough, but the actual jump, the transition from the surface of the water into the air, kind of like the transition from the on-ramp to the highway, is what you are, paying for when you supply this latent heat of vaporization. Okay, well, if this explanation was total nonsense to you, don't worry about it. Just latent heat of vaporization, there's the number. Let's do a math problem.